get copies of error. Para quienes no saben, estamos haciendo un workshop acá, o sea, digamos, nos han prestado el viaje para hacer un workshop sobre información cuántica. Tenemos invitados internacionales y algunos de ellos han aceptado dar una charla a la tarde generosamente, así que bueno, uno de ellos es Armond, que nos va a dar esta charla que nos pareció que podía ser interesante tanto para físicos como para gente de computación. Thank you.
Right, thank you. First, I wanted to thank all of the support staff for inviting me to come here. It's been wonderful to come. Thank you for coming to this little lecture. I hope I can say something interesting. I was looking at this. It's a horrible title. It's descriptively accurate, but it's a horrible title. Desiderata for an analysis of computation and problem meaning it. I thought of a better title. A better title should have been an opinionated introduction to analyses of computation, much like David Armstrong's opinionated introduction to universals. This talk I've never given before. For me, it just kind of came out of a set of notes I made for myself when I wanted to learn about computation and what people have said quite generally about computation. And the reason I got interested in this was because I was interested in certain kinds of explanations that people were trying to give of why quantum computers were faster than classical computers. And I wanted to think about whether any of that made sense, so I detoured into this literature. In any case, let me say a little bit more about what I'm going to do today. First, what I want to do is talk about the problem of providing an analysis of computation. And by an analysis of computation, I don't mean providing another model of computing like a Turing machine model or like a finite state automata or something like that. When I'm talking about providing an analysis of computation, I mean what are the conditions which are more or less necessary and sufficient for an actual physical system to be a computational system. And I want that to be an informative kind of description. In the first section, what I want to do is talk about a couple of problems that show why the answer isn't obvious. That'll have two problems that I discuss. The first one I think is kind of trivial, but it plays a role in what follows, and the second is more substantive. In the second section, what I want to do is just lay out some desiderata for what a good analysis of computation ought to do. And then in sections 3 through 5, I'll just give you a description of some various approaches to providing an analysis. And I will try to highlight their strengths and weaknesses. And this is where the opinionated part comes in. It's my opinion about whether they meet the desiderata or not. And in some cases, I will try to offer friendly suggestions to help them meet desiderata in ways which aren't necessarily part of the view right now. The other disclaimer I want to issue is that list, 3 through 5, is by no means a comprehensive list of all possible analyses of computation. But I think it hits on some fundamentally different approaches and gives you some examples of them and what any kind of view of computation needs to do. So largely the talk is a pedagogical one. I'm not trying to push a particular interpretation. Okay, with that, let's get started. So the problem. The first thing I want to talk about is the underdetermination problem. So you've got this physical system, and if you want to do a computation, you're going to have some kind of input to the computer and some kind of output. So you're going to have to interpret physical states of the device as computational states. So let's take an immensely simple system. Suppose that there are two different initial states, A and B, and two different final states, C and D. And what you need to do is you need to interpret those as computational states. Here's two different interpretations that you can give. let's let the first line represent 0, and let B represent 1, and then C0 and D1. And if you do this, you can imagine, oh, I forgot to put the dynamics in. Well, in this case, A goes to C and B goes to D. If you have the first interpretation, it computes that function. Now, if you change nothing about the system, but just something about your, description of the system, so we keep the same interpretation with the initial states, but then we change the interpretation on the other states, then it computes a different function, and this is just addition mod 2. So it's any kind of interpretation or analysis of computation typically needs to say something about how you get around the underdetermination problem. So that's one thing. But I think this is a minor problem. The more important problem, which I think really sets the stage for the problem of analysis of computation, is just this larger question. When is a physical system computing? There's a very obvious thing to try, but it turns out that the most obvious thing to try is just wrong. It won't work. So a natural thing to do would say, well, why don't we just say that a physical system is computing if we can put the sequence of states that that system enters into one-to-one correspondence with the sequence of states that some kind of paradigm model of computation enters. So a Turing machine, for example. If we can, have the states that a Turing machine enters into correspond one-to-one to the states of the physical system, can't we just say, problem solved, that's all it takes? No. And the reason why is because everything turns out to be computational. And then you've got a completely trivial notion of computation, right? I want to be able to say that things like tables and chairs are not computational. But if there's enough states around, and all you need to do is to hook up a correspondence, it's easy. Enough states, you get the correspondence, but then everything's computational. So the easiest answer just won't work. It's a non-starter. It doesn't mean that more sophisticated formulations won't work. I think they get us a long way. But the simple view just doesn't work. In order for the notion of computational system to do any work, some things can't be computers. That's the idea. So that's the problem. Now I want to give you a set of desiderata for what analysis of computation ought to do. And I claim zero originality here. These come from work that Gualtiero Piccinini has done. And you might quibble about some of these things, but I think it's a very good starting point. So let me just what they are. First, an analysis ought to be appropriately objective. An account of computation should make it a matter of fact rather than a matter of interpretation about which systems can compute a function. And I think you would also want to add about which function is actually computed. So an account ought to be objective. 2, it ought to jive well with our explanatory practices. We like to explain systems in terms of the computations that they perform. So, we like to explain the behavior of certain systems in terms of program executions. And you should be able to say how that's possible when you give an account of computation. The right things need to compute. So paradigmatic examples of computers need to turn out to be computers on whatever medium. This is not a radical desiderata. This is a completely uncontroversial one, if there ever was one. Okay. And the other side of that particular one is that wrong things should turn out not to compute. So tables, chairs, things that we don't think are computational had better turn out not to be computational on any satisfactory analysis. Then miscomputation. And this one turns out to be surprisingly powerful. We like to say say in certain cases that some kind of system was computing a particular function, but then a miscomputation occurred. Something went wrong in the process. So an analysis should be able to allow for the possibility of miscomputation in some kind of way. And then finally, an analysis of computations should give you some sense of different powers of computational systems and give you a sense of why different systems have different kinds of computational abilities. And that's it. I think these are the kind of fundamental ones. These are the most important ones. And what I'd like to do next is just take a look at how certain views of computation meet or fail to meet those Desiderata. So the first one I want to talk about is the semantic view. And I mean, we've seen this slogan that came up at the conference earlier, no computation without representation. And the idea is that computational states need to be representational states. And then, you know, some kind of account is owed about what makes a state representational. But if you go this way, you know, look, the easiest way to make something representational is to add a person or add a user. It's a very natural thing to say, and if you do this, if you make this kind of restriction, you don't have pan-computationalism. Not everything is a computer. And there's kind of cheap explanation why. You know, why isn't chair computing? And you say, well, I don't interpret it computationally. To my mind, it doesn't seem very satisfactory. Two, there's not going to be any underdetermination. Why? Because, well, the computer is going to compute whatever things we interpret it as computing. And we can just stipulate in case what it's computing. Does it meet explanation? Well, maybe, maybe not. I'm kind of undecided on this one. There's certainly no reason why you can't say that a particular system is running a program and talk about behavior that way. But I don't see quite how just stipulating that the states that a system is in are computational states, that it gives us any kind of robust sense of explanation outside of pure verbal label. But I think that's okay. Let's just call it an advantage. I think there's other problems which are far more seriously. On most accounts, well, the only kinds of accounts of representation that I know that work require something like a user or a person, a mind that has some kind of intrinsic representational capacities. But then this fails objectivity. Right? Look, here's the intuition that I have in my brain when I think about the semantic view and whether it meets objectivity. I like to think about a world in which there's only a Turing machine chugging away at some kind of computation, but there's absolutely no people around whatsoever. My intuition is that would still better turn out to be a computational system, even if there's nobody around to stipulate, here's certain computational states, and here's others that aren't. So I think that the real death blow to this view is it just inappropriately depends on us. There's other things, though. It fails right things compute. Well, I guess these two are related. And think about the exact same example I had. I kind of think of a Turing machine, or whatever, desktop computer, an iPhone, whatever. I tend to think about if that thing were doing what it normally does and nobody else is around, then somehow that's still computed. And if you don't have anybody around which can say these are computational states, these are representational states, then it turns out those things don't count as being computational. And that strikes me as insane. Hence the opinionated introduction to analyses of computation. Taxonomy. I think the semantic view doesn't give you any insight into how to pull apart different systems and say this is why this one's a better computer than another. And I think there's a reason for this. And one of the reasons is I think the semantic view as a standalone analysis of computation just won't work. It needs to be supplemented with a lot more substantive view than just computational states or representational states in order to actually meet any of the desiderata. So I think the right way to think about the semantic view is just something you might want to add on to certain kinds of analyses of computations to see whether it's a useful complement or not. All right, that's the kind of simple one. Now I want to have a look at causal views, which are considerably more sophisticated and I think more substantive. I think probably the best one is due to Copeland in his 1996 paper. So there's a long definition, and I'll read it slowly, and I'll try to explain what he has in mind. Entity E is computing function f if and only if there exists a labeling scheme L and a formal specification of an architecture and an algorithm specific to that architecture that takes arguments of f as inputs and delivers values of f as outputs, such that that pairing is an honest model of the architecture. So an architecture is just going to be a primitive set of operations. Okay? So if you're thinking Turing machines, you can move left, you can move right, you can write, you can erase. That's it. Or I guess you can update your state as well. That's what he has in mind by an architecture. And of course, an algorithm is just a set of instructions for putting together all of those different primitive operations. Now, what does he mean that it's an honest model? Well, I think the best way to think about that is in terms of the truth of various counterfactuals. So in order for this thing not to fall prey to that objection we started with, the state-to-state view, if I've got enough states, I can just cook up any kind of correspondence and computation comes cheap. Well, what he means by that is that not only do you need the correspondence for a particular instance of a value of a function being computed, but you also need the right counterfactual behavior such that if I were to put in a different value of the function as an input, it would also output the correct value of the function at the end of the computation. Why causal? Well, precisely because a whole host of counterfactuals need to be true in order for something to be an actual computational system. So the reason why the initial problem, is no longer a problem, or at least much less of a problem, is that it's not merely a one-to-one mapping that you have to do. It has to be the one-to-one mapping for a particular computation, but then the system also has to have a host of counterfactuals true of it. And there isn't a simple mathematical trick where all you need is extra states and you can interpret the system as behaving counterfactually in that way as well. At least it becomes much more difficult. And that's what you want. So that's the main idea. I think it has several objections. One, it's perfectly objective, right? So there's this claim, a system is computational if there exists a description of a particular sort, the sort that we saw on the last screen. That's something, the existence of that description doesn't depend on us at all. If we were here, great. If we're not here, doesn't matter. The description of the system in those terms would still exist. So it really does meet objectivity. And there's no epistemic limitation either. It's not as though one has to know that a certain system meets a certain kind of description in order for it to be computational. It's computational regardless of what we might know about it. An explanation. Well, the explanation of the capacities of the system are going to be given in terms of the particular algorithm and architecture that fits the system. So it seems to me explanation quite well. You can talk about a physical system executing a program in this very straightforward way. write things compute? Well, I mean, take any example of a computer that you want, and you're going to have a certain kind of computational description which will meet that system. I don't think there's any issues about getting paradigm examples of computation right. Taxonomy. Well, here I think it kind of works in the sense that you can think about all of the different kinds of computational descriptions which might meet a system. And insofar as a computational description is applicable to a system, it's going to bring with it a certain set of capacities. And when certain kinds of descriptions just fail to be instantiated by a system, then the corresponding capacities are absent. So I think there is a sense in which it tells us something about why a system has the abilities that it does. And it's associated with it being able to execute certain kinds of algorithms or instantiate certain kinds of architecture. So I think this works pretty well. What are the drawbacks? One is obviously computational underdetermination. And it's kind of not just underdetermination, it's kind of like computational redundancy. So if we look at the first example, the one that I used to set up the underdetermination problem, I think Copeland would say it's not only underdetermined which of the two functions that system is computing, it's computing both of them, is what it would have to say. So there just isn't going to be a fact of the matter, or at least a unique fact of the matter, about what function the system is computing. And in fact, for any function that it's computing, any system can be interpreted such that it's computing all of the partial functions of that as well. So you're always going to have multiple instantiation of architectures and functions. That's kind of a generic thing. I don't think that's in any way, shape, or form a death blow to the view. There's a few other objections. The claim is that wrong things will compute. It doesn't distinguish between computing a function and instantiating a function, and then it fails the miscomputation desiderata. I thought these things were too complicated to talk about in bullet points, so I make slides out of each of them. So, wrong things compute. Okay. Well, there's no restrictions that Copeland places on primitive operations that are allowed in algorithms. Couple that with the fact that algorithms can have a single primitive operation, and this is what gets you to wrong things compute. So you have things like planets can compute their orbits. What's the primitive operation? Well, it's just the orbit itself. You just have one operation, but lo and behold, planet computes its orbit. You want to know what the orbit is at a later time? Go away. That's it. So, and of course you can play this game for just about any physical system that evolves over time. So, this is a problem. It seems like everything computes on Copeland's view. I think there's a response. I think it's actually a good response. The kinds of things that ought not to compute, what it can say is that they don't compute in interesting ways. Okay? In order to get everything being computational, you have to have these ridiculous algorithms. And I don't even know if you want to call it an algorithm, where you have a single primitive operation, and you just execute that once, and that's it. So I think that's actually a pretty good response. You can say, well, yeah, everything computes, but not in an interesting way. And there's a kind of internal measure about whether it's an interesting way or not, and that's the complexity of the algorithm associated with it and the architecture as well. So I think there's a pretty good response there. And then there's another response that you can add here. There's a distinction that people make in the literature, and I didn't promote it to a desiderata, but I thought it was an opportune time to introduce it here. That there's somehow a difference between instantiating a function and computing it. You might say that planets instantiate the function associated with their orbits, but you might want to say they don't compute it. And we ought to be able to make that distinction. And there's a way to do that that's pretty straightforward. You just demand that you don't take any algorithms into consideration which don't execute an operation at least more than once. You either have a single primitive operation that you execute twice, or you have at least 2 primitive operations that you execute sequentially, or something like this. It sounds like kind of a parlor trick. For me, that response would be sufficient to distinguish between instantiating and computing. Tells me that it's not actually that interesting a distinction to make. But you can make it on Copeland's view. And it also could give you another way to rule out a lot of systems as being computational that aren't. So if you demand that you have at least 2 primitive operations, or that it gets iterated, then planets turn out not to be computational anymore. A lot of the stuff that shouldn't be computers turns out not to be computers if you import this distinction in Copeland's view. So it's something that you can do. Again, for me, if you can make the distinction so truthfully, I don't care too much about the distinction. But that's a friendly way to help out Copeland. The next consideration is that Copeland's view doesn't allow us to say anything about miscomputation of the finding. It seems impossible on the view. Why? Well, either a particular computational description will actually fit a system or it won't. And it seems like if you get the function wrong, then that computational description just won't fit the system in the first place. So there is no room in the view for miscomputation. There's no way to characterize a system as being computational unless it does its job right. That's the worry. Okay? I think there's several ways to respond to this worry. I don't think it's exactly damaging. Here's a few ways to do it. It might be the case that you can say, well, normally a system computes the function, but sometimes it doesn't. Meaning, for some range of cases, the computational description associated with the calculation of a particular value of function is apt for that machine, but through some circumstances, I don't know what, maybe somebody throws water on the computer and everything gets screwed up. I mean, it can be as simple as that. That's one way which you can characterize miscomputation on the view. There are others. You can say, well, look, the computer was built to do a certain kind of thing, to meet a certain kind of computational system, but it just doesn't. And that's another way to talk about miscomputation on the view. And then there's just the mistaken person. The person thinks an honest labeling scheme exists, but it really doesn't. So here, what I'm doing is exploiting the fact that there's a person that needs to, well, one way that you might think about this computation is that it's a judgment that we make. These are various ways in which we can make the judgment, which are completely friendly to Copeland's view. All right. So I want to also take a look at another causal view. Here's the basic idea. Just like what we started with, in order to have a computational system or to interpret a system as a computer, and to interpret it as computing a function, you need to have some sort of interpretations of the state of that system in terms of inputs, another interpretation in terms of outputs, and here is the kind of diagram that Schutz gives us. So imagine this down here as being the physical system, which you want to check if it's computing a function or not. So you've got a set of states here, and you've got an interpretation function which takes you to the range of the function you're interested in computing. Play exactly the same game for a set of output states. You have an interpretation which takes you from the states of this putatively computational system and maps them to the range of the function. I'm sorry, I said range over here, I meant domain of the function, and this is the range. Now, what's going on here? We're going to have some kind of theory of the system that you want to check if it's computational or not. And what you want this theory to do is map these computational states in the right way to the output stage such that the value of the function that you indicated is associated with this mapping. It's just a formal way of saying something that you already know. You've got to interpret the states right, if the right functional behavior is instantiated by the system, then you're good. Here are his criteria. A function f is realized by a physical system S, describable in a theory P, if and only if the following conditions hold. And I'll explain these. There exists a syntactic isomorphic mapping I from the input domain to the domain of the function. There exists a syntactic isomorphic mapping O from the output domain of S to the range of F. And then finally, there exists a function F that describes the physical property or behavior of S for the given input-output properties. That is to say, F is a mapping from the input domain of S to its output domain, described in all of the language and by the laws of P, such that for all X in the domain of F, the following holds. So, the syntactic isomorphic mapping stuff, I'm not going to get into it. It's supposed to be a way of dealing with the underdetermination problem, but I'll explain why there still is an underdetermination problem. So forget that stuff, it's not really important. 3 is where the action's at. And look, it's a causal view because, again, you need certain kinds of counterfactuals to be true. It's not just that you need the mapping for a single evaluation of the function. That mapping needs to work for any evaluation of the function that you need to do. And this gets us away from the problem that we had at the beginning, that you can just cook up a mapping willy-nilly. So, what are the advantages? Well, meets objectivity. Either this kind of description is around or it's not. Again, you have no problem with the paradigmatic examples of computation coming out of computation. You can talk about miscomputation in exactly the same sense as you could with the fix I offered for Copeland, so I'm going to count that as an advantage here. What are the disadvantages? Fails explanation. There's no way to even talk about executing a program here outside of the sense that you get the inputs and outputs perfectly right. You're just talking about the bare functional behavior of the device. You're not opening the box in any way, shape, or form and saying, yeah, and it happened to have this particular input-output behavior because there is a program, and this program does this and that and the other thing. There's just no room for it on this field. In many ways, this is a kind of black box Copeland kind of view. No natural way to distinguish instantiating from computing. Copeland's, there was actually a natural way that you could do it. Here, I just don't see any room for it whatsoever. Run things compute. Why? Well, again, you're going to have trivial kinds of, there's no restrictions on inputs whatsoever, so you can cook up the right kind of mapping such that you get computation in the wrong cases. And one of the things that we did with Copeland is that we used this distinction between instantiation and computation in order to rule out a lot of the bad things that we didn't want to see were computational, but nonetheless turned out to be computational. Can't do that in this view. Taxonomy, I don't think it really tells us much about taxonomy, certainly not in the way that Copeland's does. It'll indicate that computers have different capacities, but I don't think it gives us any resources for saying why they have different capacities. And then the problem of computational underdetermination. So Schütz actually makes a big deal in his paper about defining these syntactic isomorphic mappings, and it's a bunch of nonsense. You can see from the get that this is going to suffer from the problem of underdetermination because it relativizes claims of computation to a particular theory of the system that one's interested in. And insofar as you can have different theories of the same device, it can compute different functions simultaneously. So you've got underdetermination. Now, again, I don't think underdetermination is actually that serious a problem, but this is something that people worry about. All right, so those are the causal views, and I want to now describe the mechanistic view of computation. And the mechanistic view is associated with Piccinini's work. It has a kind of predecessor with the work of Cummins. At first, I really didn't like the view, but it's grown on me because it turns out to be, at least in my mind, far more flexible at least than I had originally anticipated. So let's see what you think. It's a little complicated to get going. A system computes when it admits of a special kind of mechanistic explanation, a computational explanation. What's that, you say? Well, a mechanistic explanation of the system S is, quote, a description of S in terms of spatiotemporal components of S, their functions, and their organization, to the effect that S possesses the capacities it does because of how S's components and their functions are organized. Mechanistic explanation, the ubiquity of it was kind of first pointed out in a dramatic way by this very well-known paper by Machamer, Darby, Craver. And since then, it's had enormous range of applicability, and Piccinini appropriates that view of mechanistic explanation and say, well, let's take that as a basic framework, add some extra stuff to make it a special computational mechanistic explanation, and then let's make that definitive of computation itself. So what's a computational explanation? Well, a computational explanation is a mechanistic explanation whereby the components of a mechanism are required to have the function processing vehicles along specific variations of their properties according to rules. Vehicles, I don't think there's a real general definition. You get to know this by example. Qubits would count as vehicles. C-bits would count as vehicles. But even things like voltage changes in dendrites, hormones, etc. can be considered as computational vehicles. And we can consider certain kinds of systems as having components which manipulate those vehicles along certain dimensions of variation, and then have these components be organized in a particular way such that you have certain kinds of computational capacities associated with it. So, what are the advantages? There are a lot of them. Trivially, it meets the explanation Desiderata because you make explanation definitive of computation. Second, obviously, the right things turn out to be computational because it turns out that, yeah, all of the things that we think are paradigmatic examples of computers do seem to have components that are organized in a particular way. We talk about them processing certain vehicles sort of in accordance with certain rules, so it seems like that's all good. Wrong things do not compute, so the tables and chairs aren't going to do it because they don't have components which are functionally organized, which have as their function to manipulate vehicles according to certain rules. So it rules out a heck of a lot of stuff in a much more robust way than Copeland does and certainly shoots. So I think it does a very good job of doing that. Miscomputation is very naturally handled here because you have a computer, it's got a functional organization, the components have a particular function, and if they fail to meet that function, then that's when you judge a miscomputation to occur. So it's very natural in the view. You can talk about taxonomy in, I think, a really nice way. In terms of the functional organization being associated with certain kinds of capacities, more complicated functional organizations can be different kinds of capacities, and you can talk about relations among them. There's not supposed to be any computational underdetermination. Insofar as the components have particular functions, you can pick out which one is correct. And you can also make the distinction between instantiating and computing. So a particular component, if you just have a single component in your computer, you might say that's just instantiating a function. But insofar as computers are required to have multiple components which are functionally organized, you can say, well, it's only those kinds of devices which are actually computing instead of just instantiating. Disadvantages, and I think this is one that Piccinini doesn't recognize, but I think it fails objectivity. And the reason it does is that components of the device don't just have functional behavior on the mechanistic view. It's crucial for there to be a particular function associated with it. Now, there's only two ways that I know of associating a function with something. One is to have it be associated with intentional design. We design it to do a certain kind of thing. And the other way is to be a product of natural selection. And obviously, you know, the systems that Piccinini has in mind are generally not of the second kind, but we build them to do certain things. But once that's what's required for something to have a particular function, then if we go away, or if we didn't, you know, if we went away, then the computer would fail to have the particular functions that it does. And I think there's a sense in which you can still maintain it has a certain function, but it'll be exactly the kind which is subject to the underdetermination problem. There's a solution. I think it's an easy solution. It's one that fits very well with the view. It's just to relativize computational explanation to functional behavior, such that with any kind of particular functional behavior, you're going to face the problem of underdetermination. There's going to be a host of different functions that you might pick out some functional behavior of the system as instantiating. So there's going to be multiple computational explanations that could be associated with the system, and hence you're going to get multiple functions computed. But if that's the only thing that takes to fix the view, to remove any of the disadvantages, I think it's a price worth paying. So let me, I already said that. If you go this route, it has a minor drawback. One has computational underdetermination. So let me just wrap up. I don't think it's possible to meet all of the constraints. Something's got to give. The thing I think needs to give is just computational underdetermination. I don't see it as any sort of massive problem to have computation underdetermined. I think it can, you know, whatever is useful to us is good enough for singling out which description to use. I don't really care about underdetermination. And right now, I think the mechanistic view with my friendly modification best meets the Desiderata. Although I think Copeland's view is very much a live competitor. Well, I'll just wrap up there. Thanks.
Comments and questions?
About objectivity. If you have a commonly recognized computer and computing, how do you know that it's a computer? Because it's only zeros and ones being manipulated. I fear the identification of the thing as a computer depends on interpreting it as a computer. That knowing what the variable names try to suggest is the source code. And there was a Dilbert joke I recently found when one of the collaborators in the working place was accused of having porn photography in his computer. And he says it's only zeros and ones. So there's no photo at all. Those guys who saw the photos converted the information into photos. I am not to blame. So there's inevitably a subjective aspect in computing and interpreting things as computers.
So I guess here are a few thoughts about that. There's always going to be room for interpretation because of computational underdetermination. That much is certainly true. But I guess, you know, either we have a strong intuition here or not. And my kind of intuition is really the one that I stated a few times, that if there's a Turing machine chugging away and there's nobody to interpret which computation it's doing, it's still computing, in my mind. But I have discovered that not everyone shares that intuition. This is the youngest thing about philosophizing, right? But that's all right. I you know, if you say we need some sort of semantic element here to do some sort of work. I'm kind of open to that, but I think the only real work it's going to do is solve under determination. If you want to do any more serious work, you need more resources than just an interpretation. You need more structure than that. So, you know, I think we can just say, well, if you've got this intuition, then go this way. If you've got another intuition, this is the other reasonable option. I don't need to do any table thumping.
So on this particular example of the lone Turing machine, my colleague Owen Moroni has quite a cute way of putting the point. So in the foundations of statistical mechanics, we used the idea of Boltzmann's brain, which is from a very high entropy, the hypothesis from a very high entropy state of the universe, suddenly you have spontaneous fluctuation in the brain comes into being with traces in it, which would be memories and so on. And then the comparison case here is Boltzmann's laptop. You've got either just fluctuating out of the after popping out of a white hole and then falling into a black hole, and there's nobody else in the universe. So that's quite a cute way of putting the point. For what it's worth, my intuition is annoyingly the opposite of yours here. So I would say that thing isn't a computer, and I'm trying to explain away the thought that it's not computing. I'm trying to explain away the thought that it is computing by saying, well, we would be able to use it as a computer if we were in that universe too. So that's why we're inclined to say that it's computing, because we could use it, and there's an important fact about it that we could use it. But even so, it's not computing, or maybe not. So,
you know, like, much like some of the points yesterday, the points I made with you, I'm more inclined to just take the kind of Mellement approach in these kinds of cases where, well, okay, you know, here are the two possibilities. I can't say anything about, I don't have any, you know, important argument about why you should have my intuition rather than yours, and I also don't think much is at stake. So I'm happy to just say, well, it's this way or that way, here are the reasonable options. So if it does make a difference, I'd like to know. That would be the really interesting thing.
I think that's important. And the other minor comment I had is that on Semantic View, it looked like it was a big problem for it, that it was not going to help with the computational explanation and taxonomy things. But then I was wondering whether you might say that, well, if the question is just which objects are computed, then it needn't be that an answer to the question what objects are computing is also going to tell us automatically and what's the interesting structure of their computation. So it just seems to me that perhaps one would add that it's not ruled out for the semantic people to say, and look, I can tell you this further story about the structure of computation which is linked to functional organisation.
I think it depends on just what kind of demands that you see an analysis of computation doing. If it's meant to be merely a sorting mechanism, this is the computational stuff, this is the non-computational stuff, then none of those objections that are raised are actually going to stay. But I take it, analysis of computation should do more than that. It shouldn't just merely be a sorting mechanism. Again, I think the semantic view it's not really a standalone view. It's just something that you might choose to add or subtract to any other view. And, assuming that people want more than a sorting mechanism, and I think they do, it's a tag item. You can add it to any of the views that I mentioned, and you'll resolve under determination every time you do it. But I think in a cheap way. But that's all right.
Yeah, I agree with you that I think it's impossible to meet all constraints, and I think it's because the computational under determination is in some way opposed to objectivity. I heard what you said about if a Turing machine computes a function, it also computes all partial versions of that function, and that's true for all computing systems. And if you don't give an interpretation of which of the functions is correct, then you have underdetermination. But I agree, I think that's not a problem at all. All of us uses computational systems that maybe are underdeterminated and give them different interpretations, and it treats all of our needs. I think some program that I have here, I can use it for compute a certain function, and the others can use it for another function, and it depends on the interpretation, and we can live with that. I think I can sleep.
Yeah. I mean, the other way that you might go there is to address the underdetermination problem, not with the sole resources of analysis of computation, but appeal to use and say, look, an analysis of computation, barring the semantic stuff, just won't tell you which function it's computing. It'll give you a range of possibilities here, and that's good enough for doing all the things that you want something to do. But if you want to figure out what it's being used to compute, then you just need to look at how someone uses it, and that's going to pin it down. It seems to me that's totally reasonable. I have no objections to doing that. But I would say it's not somehow intrinsic to computation to pin it down. It's something that might be pinned down pragmatically.
But the universal Turing machine computes all functions. It receives a function as an input, and another input, and it computes the function received as an input.
Yeah, I mean, so underdetermination still comes in there, right? Because there's isomorphic functions, and
yes.
A stipulation.
That's the
point. This one rather than an isomorphic one.
Yeah.
There's just one remark which is related to this remark, which is that if you take, for example, an semantic theory, there will be an infinite amount of theorems. Most of them, you can give a definition, a finite sequence of logical steps, which give you a lot of true propositions according to that actions. But most of these theorems are not interesting. So there's a problem in mathematics which says, well, what is true mathematics? So in that level you have that problem. And it is completely unrelated to the physical problem. The same in computational computation. You have, if you define a program, what is a program? There are lots of silly programs which can be defined as programs, and they do not compute nothing. So I remember that you said, well, I have a problem, and it is a kind of disadvantage of some interpretations, which is, well, I don't want a table to be a computing machine. Well, that is very similar to the problem of I don't want that this kind of silly proposition is a theorem. That is why you call them proposition, not corollary, or you put theorem, which is an important step in mathematics. And for example, you have your programs in your computer are interested for you, but from the formal point of view, they have no difference with many abstract programs which satisfy the same properties, and they are completely silly programs which do not. But very surely, there are much more abstract programs that silly things in the world going on, because the quantity of functions they have, they can conceive are infinite in a very deep sense. So my question is, the kind of underdetermination that you have here, and the kind of impossibility to define things in an objective way or something like that, has a deeper root in logic and in mathematics. I mean, if you want to pose the same problem in a logical way, you will have the same problem. You don't know how to define what is an important problem or what is a function. You have a lot of silly functions going on there, and silly Turing machines.
So,
you understand what I mean? I mean, you don't want this to be a computer. but maybe there's a silly Turing machine which the logical correlates of this silly thing. You see, there's a logical problem going on here.
So I think there's kind of one thing that I would agree with and another thing that I wouldn't agree with. What's silly and not silly, I think, doesn't have anything to do with what's computational and not computational. But what you might say is that, look, especially when we're talking about whether a certain function is computed in the world, this is going to inherit any kind of limitations in the mathematical description of that function in the first place. So, you know, and it's just isomorphism in mathematics, right? Mathematics determines the structure up to a certain kind of limit. And, you know, any computation of that function is going to have the same kinds of limits that mathematics has. That is something I would certainly agree with. And you could say, you know, look, a lot of the end of the termination is coming from that kind of feature. But I don't know if that's what you have in mind. But the silly, non-silly stuff, I don't think that has anything to do with computation in physical systems and making that judgment. Now you might say it's doing a stupid computation, but I don't think it's the job of an analysis of computation to tell you what are the useful ones and what aren't. I think that's just pragmatic. But that's going to depend on us.
But I think that the kind of computation, my intuition is that you cannot escape the kind of pragmatics just in this particular.
Well, I gave you some ways to do it. I don't know if you like it.
Short thing. I didn't. I heard you talked about miscomputation as giving the wrong value or giving none. And I want to step on there a little bit because one of the first things they teach us, computer scientists, is that programs may not end, and there are still programs. How do you think these views take into account the possibility that a computing system may not give any value and still or not be comprehended in the computing paradigm?
Yeah. Well, let me talk about it on the mechanistic view.
Yeah.
So the mechanistic view would probably say something like this. If the computer gets stuck, right, what happened is it had a job to do, a particular component had a job to do, a function to realize, which was supposed to be to manipulate a vehicle in a certain kind of way. And for whatever reason, that thing didn't get manipulated in the right kind of way, or if the computer's somehow stuck in a loop where a vehicle keeps looping around the components, but it never makes it to the right component to give you an output. So I would say that's probably what they would say. And
yeah,
I
think the Causal view has this problem because it talks about output, and it talks about output as something that always happens. But maybe you want the computational system to handle. Maybe you want to compute division, and if you give division by 0, you want the system to not give any answer. That's not miscomputation. That's even indetermination of the function you gave.
Sure. I mean, I think, depending on what you want the machine to do, that wouldn't count as a miscomputation, right? You want it to just give you an error message, right?
Yeah.
But that wouldn't be a miscomputation in the sense that Piccinini intends. It's when, for some reason, the functional organization and the rules associated with those components and whatnot, something didn't work right.
Yeah.
The function wasn't, and what I mean, the function wasn't appropriately realized. I mean, it has two readings here. One, you didn't get the right output, or you didn't get any output at all, and then the deeper reason is because the function of one of the components, or of many of the components, wasn't realized in the right way. So, we shouldn't equivocate on function. It has two senses there. The explanation the mechanistic view gives is the function of a component wasn't realized right, and that's why the function that you were computing wasn't realized. Thank you.